So thank you everyone for showing up to this final lecture in the bootcamp series. Once again, I'm very pleased to introduce Ankur Moitra from MIT. He'll be completing his excellent series on learning in high dimensions. So please take it away, Ankur.
Great, so thanks everyone for making it all the way through until the end. So today I'm going to ask a somewhat conceptually different kind of question that I asked in the first three lectures. So in the first three lectures, I gave you a variety of different techniques for designing provable algorithms for high dimensional learning problems. And these were mostly problems that were motivated by data science, things like, learning mixture models. Sometimes the motivations came from other neighboring domains, like in phylogenetic reconstruction. And then we talked about, how to deal with robustness, both in unsupervised learning contexts and in supervised learning contexts, like when you want to learn some sort of decision boundary. But today I'm going to ask a qualitatively different sort of question, which is whether these types of tools, specifically things that have been useful like tensor methods for designing provable algorithms, might also be useful in neighboring disciplines like physics. So I think this talk really comes from the fact that I sit in a math department, so I see all kinds of applied mathematicians working on inverse problems for, in engineering problems. And a lot of these engineering problems, they really seem to me to resemble a lot of the types of problems that we do study, at least conceptually, within theoretical machine learning. So I'm going to ask their proof algorithms have something interesting to say. In fact, I only really know one example, so let me tell you something about a particular inverse problem that shows up in physics, specifically in optics. So of course, I expect most of you probably aren't familiar with a lot of optics, but let me explain the setup. So in optics, you're thinking about observing some object through an optical system, usually a lens. And you can think about this maybe in the context of astronomy, that this object is so far away that you can basically treat it as a point source. Now it's luminous, so you observe light from this point source. And you need some sort of model of the lens, and usually you model it as something with a circular aperture, and that's a very good approximation in most settings. And you also need one more key property, is that the light that you're observing is incoherent. And when you do this, when you observe a point source that's far away through a circular aperture, you get a diffraction pattern on your observation plane. And the observation pattern that you get from a single point source is called an Airy disk. So let's talk about what an Airy disk is. Well, first, let me define it as a function. So an Airy disk involves Bessel functions. So you take a Bessel function, J1 of the first kind. It's not really important for this talk what exactly it is. And there's also a parameter sigma that you should think of as controlling the blur. So in fact, the larger sigma is, the more that this point source is blurred out. So this is what the Airy disk is. It's some function that depends on these Bessel functions and this blur parameter sigma. Now, if you think back to the physical setup in optics where you have a lens, well, actually the properties of your optical system are the things that determine the amount of blur that you observe. So things like the numerical aperture for your lens are things that go into how you should think about sigmas being set. Now, one thing to keep in mind is that these Airy disks are pretty interesting objects. If you look very close to their center, they look a little bit like a Gaussian. They have a peak at the center and then they decay. But then they're actually a little bit different because they have oscillation. And you can see these different rings occurring, and this is called the Airy disk. And there's a nice interpretation of what this Airy disk means. Well, you can do this through Feynman path integrals, but what it is this Airy disk function tells you the infinitesimal probability of detecting a photon at some position in the observation plane. So it's literally a sampling model where you're thinking about sampling photons from this underlying diffraction pattern that's itself a density function. And this diffraction pattern was actually first computed way back when, back in 1835 by Sir George Biddle Airy, and that's why they're called the Airy disks. So now, what is the diffraction limit? Well, it's a rough idea in the first place, which is that, for more than a century and a half, really since Airy's work, it was widely believed that this physics imposes some kind of fundamental limit onto resolution. And so the way to think about it is, what if you're observing not one point source, but 2 point sources? Well, that's going to create a superposition of Airy disks, a mixture of Airy disks. And that's why it's important that these point sources are incoherent, is that they don't actually interfere with each other. So instead, you just get the superposition of these two density functions. And the idea is that as you take these point sources and you move them closer and closer together, eventually it seemingly becomes very hard to tell whether it's a single Airy disk or it's two Airy disks. So this problem literally arises in astronomy, where you're looking out in the night sky and you observe a star, or what you think is a single star. But you have the problem that it's very hard to tell whether it's one star or it's actually a double star, because two things are very close by to each other. So the main question that I'll be interested in is there a way to actually make this rigorous? So instead of just heuristically believing that when they get closer and closer together, it seems hard to disentangle these two Airy disks, what we want to understand is whether there really are hard and fast statistical and algorithmic limitations that arise when we want to estimate a mixture of Airy disks. And this is what I mean when I say we want to study statistical and algorithmic foundations for the diffraction limit. So actually, another funny quirk in history is that not only is this diffraction limit a somewhat fuzzy concept, but when people have sat down and tried to figure out what exactly is the fundamental limit, what ought it be, they've come up with a variety of different answers, since Airy's original work. So in particular, people have studied the question, what should be the minimum separation that you can hope to resolve in this kind of setup? And how does that minimum separation depend on the parameters of your optical system? So in some contexts, this means, if I want to build a larger lens, well, how much more resolution power does that actually buy me in terms of being able to resolve closely spaced stars in the night sky? So about 30 years after Airy's original work, Rayleigh suggested a simple criteria that I'll talk more about later, that he said that it's only possible to resolve things which are roughly 1.22 times pi times sigma separated from each other. So that needs to be the minimum separation between the centers of the Airy disks, because otherwise he believed that it's just impossible to actually try and resolve beneath that threshold. And actually, there's been a lot of work over the years suggesting many different criteria, which lead to many different constants. And the question that I want to ask is, which, if any, of these criteria is the right one? And is there a way to make this problem mathematically rigorous and understand what the diffraction limit ought to mean? So it's fun to dig into some of the history. Actually, my student Sitan, managed to find all of these amazing gems in the physics literature and dig into why they thought the diffraction limits were where they were. So back in 1879, Lord Rayleigh proposed that Rayleigh criteria, and he proposed it really just as a heuristic. He said the rule is convenient on account of its simplicity and is sufficiently accurate in view of the necessary uncertainty as to what exactly is meant by resolution. So he meant it just as some sort of rule of thumb about where you should draw the line between what you can actually resolve and beneath which you should just think about as being noise that you can't hope to figure out what's going on. But over time, people thought that the diffraction limit ought to actually mean something much sharper, and they came up with different constants. There were all kinds of refinements to Raleigh's criteria, and they were all based on varying degrees of rigor. In fact, one of my favorite quotes here is due to Carroll Sparrow. So this was back in 1918. So not only did he suggest a different criteria than Raleigh's criteria, but he was rather bold about it. So he said, it's obvious that the undulation condition should set an upper limit to the resolving power. Actually, that's a recurring theme. You'll see that in many of these quotes, people will say things like, it's obvious, without actually supplying any mathematical argument. In fact, he goes on to say, to give a proof in his own way, that my own observations on this point have been checked by a number of colleagues, friends and colleagues. So, that's his argument, is that if you can't see that this is the true diffraction limit, then, everyone else can see it, my colleagues and my friends. And in fact, over the years, some people have even pushed back on the idea of there actually being a diffraction limit at all. In fact, there's this beautiful quote to Feynman in his famous Introduction to Physics lecture series back in 1964, where he said, when discussing Raleigh's criteria, well, it seems a little pedantic to put such precision into the resolving power formula, actually, if sufficiently careful measurements of the exact intensity distribution over the diffracted image can be made, the fact that 2 point sources make the spot can be proved regardless of separation. So he's pushing back on this idea that, he's really saying that you can actually go beneath the diffraction limit if you really want to, specifically in a case where you just have 2 point sources and that there aren't any fundamental limits to learning mixtures of two Airy disks regardless of their separation. So it's kind of a subtle thing because over the years, different communities that rely on optics, they have their own beliefs about which of the criteria are the right ones. There are different criteria that are believed when you're talking about resolving inside the cell versus resolving stars. And nevertheless, there is actually a lot of empirical evidence that, for some types of systems that we're trying to observe via optical systems, there is a limit to what we can resolve. So can we put this on a rigorous foundation? So let me tell you about some recent results. And for those of you who are familiar with things like learning mixture models, there are going to be a lot of parallels between the types of mixture models that we study in theoretical computer science and the types of mixture models that are arising in these optics problems and these inverse problems in physics. So the first thing, this is the less surprising, the results, is that we actually do give provable algorithms for learning mixtures of Airy disks that have non-asymptotic guarantees and that work regardless of the separation. So if you have two Airy disks, if you have any constant number of Airy disks, indeed, there isn't actually any real diffraction limit. You just need to take more and more samples and run in a larger amount of time, but you really can go beneath the diffraction limit. So what we showed was that given samples from a delta separated mixture of K Airy disks, so that means that the centers are delta apart from each other in L2 distance, and these are all things that are happening in 2 dimensions because you're thinking about the centers as being locations in the observation plane. And there's a notion of a relative intensity lambda, which is really just the mixing weight. So what fraction of the photons come from which of the different sources? So as long as you have a lower bound on the relative intensity of all of the different sources, then there is a polynomial time algorithm for any constant k that takes a polynomial number of samples and learns the centers of the Airy disks to any desired accuracy epsilon and with small failure probability delta. So just to take a step back, because a lot of these theorems that I'm going to tell you about today are not technically hard, especially given all that we know, especially in theoretical computer science, about how to learn mixture models, how to learn mixtures of Gaussians and things like that. Well, I think it's still good to come back and think about how these results relate to some of the debates that were had within physics over the years. And actually, many of those arguments about different constants being the right one for the diffraction limit, they're all based on some thought experiments about what happens when you have 2 different Airy disks that are very close to each other. They all differ in how exactly close those Airy disks need to be for you not to be able to tell that it's 2. Some of them are undulation criteria like Sparrow's criteria. Some of them are different, like when they become unimodal in the middle, when they're so close that the middle hump, you can't see a double hump anymore. But because they're all based on the idea of pushing 2 Airy disks closer and closer to each other, they're not actually statistically well-founded because it doesn't actually matter how close they are. You can still resolve them if you really use the fact that it is honestly an Airy disk that shows up in these types of diffraction patterns. So there really is no fundamental limit to diffraction. There is no resolution limit. And this is making good on this assertion that Feynman had in his lecture series. Now, I think the second part of the results are, more unexpected from a physics standpoint, because almost all of these arguments about the existence or inexistence of a diffraction limit were all based on thinking about mixtures of 2 Airy disks. But actually, something funny happens when you take the number of Airy disks to be large, is that it turns out that there actually is a phase transition. So you actually can make sense of what it means for there to be a diffraction limit, because you see the difference between needing to run in poly in K sample complexity or instead needing exponential in K sample complexity. So at the same time, when the number of centers is large, there actually is an honest phase transition in what you can resolve statistically and algorithmically and what you cannot hope to resolve. So here we're not exactly going to be able to pin down the precise constant, but we're going to pin it down to within a range. So let me define two constants. Gamma plus will be some constant that depends on some properties of Bessel functions. That's this parameter J01. I won't get into what that is, but it works out to be about 1.53. And there's an explicit construction for a lower bound where you just can't hope to resolve these different separated point sources, where the separation is about 1.15. And so what we prove on the algorithmic side is that, when you talk about this gamma plus separation, if the mixture of K Airy disks has the property that its centers are gamma plus times pi times sigma separated, then there really is a polynomial time algorithm that's now polynomial in all of the parameters of the problem, polynomial in the number of centers, polynomial in 1 over the minimum separation delta, polynomial in 1 over lambda, where lambda is the lower bound of the relative tensity, and 1 over epsilon, where epsilon is the failure probability. Sorry, there should also be a polylog in 1 over delta, but there's an honest poly in K time algorithm with that number of samples too. And conversely, it turns out that beneath some other constant times pi sigma, beneath the separation 1.15 times pi sigma, then there really are separated mixtures of K Airy disks that you need exponential in K many samples to learn. So this means that if you're in some settings where you can't hope that there are few point sources, well, you really can say that for any reasonable experimental setup, there's no hope for you being able to resolve that number of point sources. Because if you think back to the original experiment where you have this optical system and you're observing these point sources, well, any reasonable physical setup has some limitations because each one of the photons that you observe is like a sample from the diffraction pattern. And ultimately in your experiment, you start counting photons at some time 0 and you stop at some time t. You always have a finite exposure time. So you're only ever observing a finite number of photons. And the truth is that beneath some diffraction limit, the number of photons you need explodes so fast that you really can say it's not reasonable to pick out where these point sources are up to better than this resolution. So I think this is a neat way that provable algorithms can contribute to inverse problems in the sciences, is that on the one hand, we can actually prove fundamental limits to the fact that, hey, you can't actually resolve at that level of granularity that you think you can. In fact, there are other types of limitations in terms of the experiment that naturally are very related to things like the sample complexity. Because the truth is that even when you observe the location of a photon in the observation plane, well, ultimately, you're going to measure its location through some apparatus, and you can't hope to record its precision, its location at arbitrary precision. At best, you can do it up to some finite accuracy. And those types of limitations in your experimental setup are actually very related to having sample complexity limitations on how many photons you can observe. Great. I think I just answered the question that was in the Q&A, which is, are you taking into account the granularity of the screen where the photons hit? So I can talk about this a little bit more later because I don't want to get too sidetracked, but these two are related because, if you only record the location of a photon up to some finite precision, then we'll see that the natural way that you try and get an approximation of the true diffraction pattern is you try and smooth the empirical distribution of what photon you observed approximately where by some kind of smooth function. So that's the same way that you cope with things like only having a finite number of samples. Both of these two things are kind of related because the underlying Airy disk is itself a smooth function. So when you don't record the location precisely, you can think about it also as being like an error almost in, along the y-axis instead of the x-axis. So thanks. Great. This will be a little bit more of a philosophical talk than usual, so let me pontificate even more, which is that, people have continued to be interested in questions about the diffraction limit for a very long time. I mean, interest has continued all through the years, and you can still find modern surveys written within the last few years about these kinds of topics. And what's really funny is that in different communities, they have different beliefs. If you're studying optics questions in astronomy, you don't believe there's a diffraction limit at all. In fact, you have great heuristics that can and do work beneath the diffraction limit. Because when you're observing these double star or single star, all you do is you try out two different Airy disks and you try out whether you find a good fit to the scattering function that you're observing by putting those two Airy disks very close to each other. If it's a good enough fit, you conclude that it's two Airy disks and not one, and that's a double star. But the trouble is that these are all heuristics within astronomy. You don't actually know that you're provably, figuring out whether it's one star or two stars. You have no way to control things like what's your false discovery rate. And at the very other end of the spectrum, you have things like microscopy, where your goal is to look inside a cell and what's going on in a molecular level. And here, the limits in an optical sense are a little bit different because you have some instrument you're using to peer inside the cell. But the trouble is that, if you really wanted to observe the cell at a finer and finer granularity, that means you need to use higher frequency light, and higher frequency light has more energy. So after a certain point, you would actually destroy the cell, the thing that you're trying to measure. So people have long believed that there are fundamental limits within microscopy, and those are settings within the cell where you have tons of closely spaced sources. And there, people really do believe that there is some kind of fundamental limit. But what they believe is the limit is somehow a bit different than what other communities do. They're big believers in the Houston criteria instead of the other things. So this is kind of neat because I think some of these provable guarantees help explain why there are such differences between these two different communities, that simultaneously there can both be no diffraction limit and yet really an honest to God diffraction limit. It's just that it emerges as a phase transition when you talk about the number of sources. And one thing I want to mention, which is actually the reason that I got interested in this in the first place, that's maybe a story for another time, but somewhat recently, back in 2014, there was a Nobel Prize in chemistry for super resolution cameras. And these super resolution cameras, are about breaking the classical diffraction limit, even though we didn't really know what the diffraction limit meant in the first place. Because what super resolution cameras do is they take the cell that you want to observe, and it has tons of these closely spaced point sources that you want to figure out where they are and what they're doing. And what you do is you chemically tag them with different kinds of chemicals so that they only respond to certain wavelengths of light. And in this way, what you're doing is you're effectively downsampling the objects that you want to observe, because now when you measure with some particular frequency of light, you only get a subset of the objects and they're better spaced. So these types of things have been, nothing short of a miracle in biochemistry, because they do some pretty spectacular things. Like you can actually see through super resolution cameras and piece together what it looks like when the HIV virus enters a cell. And that's not something that you can do with traditional microscopy and traditional optics techniques. So in fact, some of these provable algorithms, I think they make sense of, what is the rigorous notion of what diffraction limit these super resolution cameras purport to be breaking. And there's a lot more to do here to think about other physical setups and what types of inverse problems they lead to. So can provable algorithms in machine learning contribute to this discussion in optics and more broadly in physics and the sciences? I hope that the answer is yes, and let me dig into at least one positive example. Okay, so there's something else cool that you can do, which is, you can ask to visualize what these diffraction limits look like. See, I made this claim that the diffraction limit, it's not something that happens when you have two Airy disks. It's not something that happens when you have three Airy disks, but it's something that emerges when you take the number of Airy disks to be large. So let's try and visualize that. Now I'm going to simplify the setup a little bit because for simplicity, I'm going to assume that all of the point sources are along the same 1D line in this 2D space. Because in that setting, when all of the point sources are on just a single line, it turns out that we don't have gaps between our upper and lower bounds. We can exactly nail the constant. The correct constant is 1, and it's called the Abbe diffraction limit. And in this setting, what we can do is we can try out two different hypotheses. What if I vary the number of centers k, and I create one hard mixture of Airy disks and another hard mixture of Airy disks that try to look like each other? And I can ask how many samples would I need in order to solve this hypothesis testing problem of which of the two mixtures it was. And what you can see is that I'm going to plot the natural log of the total variation distance between these two different hypotheses. So really, it's the exponential of this y-axis, represents the number of samples you need, the number of photons you need, the number of precision you'd need in your measurements of the locations of the photons in order to provably distinguish between these two hypotheses. And right here along the x-axis, I'm going to normalize things so that the Abbe diffraction limit happens right at 0, because I'm taking the natural log of the separation divided by pi, and I've set sigma to be equal to 1. And you can see what happens with the diffraction limit because it's actually something visual. Because as soon as you vary the number of centers, if you take 2 centers, there is no diffraction limit. When you go way beneath the Abbe diffraction limit, how much does it change? How many samples you need in order to resolve up to the precision given by the Abbe limit, up to some way sharper precision that's way beneath the diffraction limit. It doesn't change by a whole heck of a lot. And that's why in astronomy, visually, you don't have to believe in the diffraction limit. There are heuristics that you can actually provably analyze. But in contrast, when you have something like 90 point sources, which is really not an uncommon thing when you talk about the cell. In fact, you'd have way more than that. You can see that there's an inflection point that once you move beyond the Abbe diffraction limit, well, I guess you can go a little bit beneath it if you have tons and tons of sample complexity. And if your apparatus is so fine-tuned that you can really measure the locations of these photons to some very sharp precision. But once you start going beneath that, it's just not possible. How can you measure the location of a photon up to precision in the location e to the minus 35? We're not going to do that. So, there really is a fundamental limit that happens just through statistical considerations about what you're doing. And really owing to a lot of the insights that, for those of you who are very familiar with theoretical computer science, learning mixtures of Gaussians, things like that, the story I'm going to tell you has, a whole heck of a lot of parallels to that other story. And that's what I mean when I say that I think a lot of these algorithmic insights might actually have something interesting to say in these neighboring domains. All right, so I can tell you a little bit about, what goes into the techniques because, I don't want to get too much into the techniques, but I want to at least give you an idea about why there ought to be a diffraction limit and where it comes from. And really, a lot of it is going to come through thinking about the Fourier transform and through thinking about some algorithm that's called the matrix pencil method. So let me dig into some of the ideas. Nothing here is very hard. This will actually be very simple, especially if you know some of the earlier works on learning mixtures of Gaussians. So what I claim is that the inverse problem we want to solve, we can think about it as a deconvolution problem. Because what we have before we have these Airy disks is we have their centers. So we just have these delta functions at these different centers of these Airy disks. And then what happens is that we convolve by an Airy disk. And that gives us these superpositions of these different Airy disks. Now, all of these Airy disks have the same blur because they come from the same optical system. Whatever lens you're using has the same numerical aperture. And that's why you can express it this way as the convolution of a bunch of delta functions representing the centers, along with this Airy disk function. So it turns out that there's a very natural strategy for solving a deconvolution problem, is you can just use the Fourier transform and divide. So nothing fancy is really going to happen here, but it will be slightly subtle in some ways. So let's talk about the diffracted image. So first, we have these relative intensities, the lambda sub j's. Remember, these are like the mixing weights because they represent what fraction of the photons are coming from the jth point source. When you're looking up in astronomy, different stars have different luminosities. The more luminous ones represent a larger fraction of the photons you're observing in the observation plane. That's where this comes from. And then you have these Airy disks, but the difference is that it's not I of x, it's I of x minus mu j because you're shifting it so that it's at the location mu j. And just to make sure we're on the same page, this mu j is a point in 2 dimensions because it's really its location in the observation plane, the place where you're collecting the different photons. So I said that the Fourier transform is very important, and it is. So let's take the Fourier transform. That's called p hat of w. Now it's a nice linear function, the Fourier transformation. So we get still this linear combination of these mixing weights lambda j, no surprise there. We get the Fourier transform of the Airy disk. That's going to play a really key role. But now what does translation do when we translate the center from 0 to the location mu j? That corresponds to multiplying by a trigonometric function. So instead, it's e to the minus 2 pi I. Remember, mu j is a dimension 2 vector because it's a location in the observation plane. Omega here is a length 2 vector 2 because we're working in 2 dimensions in this Fourier transform. We take their inner product, and that becomes the frequency in this exponential. So this Fourier transform is going to play a key role. And, I didn't really tell you what the Airy disk looks like functionally. I just said it has to do with Bessel functions. Well, this is analytically what the Fourier transform of an Airy disk looks like. This actually might look kind of like a mess, but the way to think about it is that what it looks like is you take the indicator function of a ball in 2 dimensions, and you convolve that indicator function with itself. This is actually what Fraunhofer diffraction tells you happens, even if you don't have a circular aperture. You take the cross section through your lens, and then you take that and you convolve it with itself, and that's the thing that describes your scattering function. Anyways, no matter, that's just some intuition about the physics. The important thing about what this function I hat of w looks like is actually very simple. All we're going to care about really is where it's 0 and where it's non-zero. So if you look at this function, I claim it's non-zero strictly inside the disk of radius 1 over pi sigma. That's the key point, centered at 0. Now, why is it important where I hat of w is 0 versus non-zero? Is because our idea for deconvolving by an Airy disk is to try and get rid of this I hat of w. Really, I want to take some approximation to p hat of w, and I want to divide through so that I kill this I hat of w term, and I'm only left with the lambda j's and these exponential terms. So that's the question that I'm after, is can we remove this I hat of w term? Now, if there are locations where I hat of w is 0, then we can't hope to divide because we're not allowed to divide by 0. So really what I mean is I want to remove this I hat of w term, but we'll only be able to query the result in the region where the I hat of w was non-zero to begin with. So this is one of the key lemmas. It's a pretty simple thing, actually, which is that what I claim is that if we're given samples from this scattering function rho of x, then what we can do is algorithmically, we can simulate noisy access to the following exponential sum where I've removed the I hat of w term. And this will be a really useful exponential sum for us because through querying it, we're going to hope to try and learn the parameters of the mixture. We're going to hope to try and learn the lambda j's and the mu j's. That's the overall goal. So, how does this thing work? And actually, let me emphasize one key thing, which is that this exponential sum, as I was alluding to before, I can't hope to query it anywhere I want for any possible omega. I can only hope to query it for omegas within some bounded disk. I'm only allowed band-limited access to f of omega. So that's the sense in which many sort of heuristics for, thinking about inverse problems in optic systems, whatever optical system you're thinking about, whether it's you have a giant lens and you're looking at stars, or it's you're sending light into a cell to try and measure what's going on in the cell, the basic assumption or ansatz is that all of these things are somehow band-limited access to these point sources that you want to be measuring. And this lemma makes it precisely clear that you literally have band-limited access. You're only allowed to query f of omega within this bounded disk. So now how do we prove this lemma, and how do you actually solve this deconvolution problem? So this thing is actually pretty easy. It's using the following simple procedure. So first, I draw a bunch of samples from rho of x. I observe tons and tons of photons, and I record approximately where they are in the observation plane. Now, that's not going to be a good approximation of rho of x because that's a discrete distribution, right? So, how should I go about using those samples to create a good approximation of rho of x, that's also continuous too, is I take a bunch of samples from rho of x, and then I take that empirical distribution and I smooth it by convolving by a small variance Gaussian. If you're a statistician, this is called a kernel density estimate. And this intuitively works, and you can prove it. Anytime you have any smooth density function, you take enough samples and you smooth what you observe, and that will be a good approximation to the unknown distribution. So that's great because it gives us some approximation to rho of x. Now, how do we take that approximation of rho of x and turn it into an approximation to rho hat of omega? Well, we just take its Fourier transform. That's it. So when I take its Fourier transform, we're going to get a good approximation to rho hat of omega, the Fourier transform of the true scattering function. And then all we do is we pointwise divide by this Fourier transform of the Airy disk within the part where it's non-zero. That's it. And this is the thing that proves this lemma. It allows us to say we can pretend that we have noisy access to this exponential sum in a band-limited sense. So now we're faced with a nice math question, which is we have an exponential sum that we're only allowed to query at some particular band-limited locations, and we have a different kind of inverse problem. Can we solve the inverse problem for this exponential sum and figure out what lambda sub j's are in it and what mu sub j's are in it? That's the real problem that we want to solve our optics problem that we started off with. So let me tell you a really basic strategy first. There's something trivial you can try and do. This is already going to give us some good algorithms in the case where we have a constant number of sources. So, I have this band-limited access to this function f of omega, this exponential sum. One thing you can do is, 2D problems, 2D exponential sum problems are actually not that easy to reason about sometimes. So one thing you can do is you can choose a line in Fourier space, and maybe you only query f of omega along that line. So that's even further restricting the places that you're accessing f of omega. And maybe just that information about what f of omega looks like along this line intersected with this disk is enough to reconstruct the parameters of the exponential sum. Now, it's good to keep in mind that we're working in Fourier space here. So what does this strategy look like when you're talking about the original image that you're observing? That's a mixture of Airy disks. Well, intersecting with a line in Fourier space is actually the same thing as projecting onto the line in the original space. So what this means is that you're taking this mixture of Airy disks. This is actually an image taken from a cell. And what you're doing by restricting to the line is you're going to project all of the Airy disks onto that line. Now, there's a big problem with that, which is that if you originally had separation delta, all of the centers of these different Airy disks were by assumption delta separated from each other. By projecting onto the line, you might accidentally make the separation much smaller. Now, it turns out that that's not going to be a big deal when you talk about only having a constant number of sources. So actually, that strategy is going to do pretty well, and it's going to work to give us the first theorem that I told you, that there is no diffraction limit when you talk about any constant number of sources. So let's try and make this rigorous. So what does it mean, and what does it look like mathematically when I only query f of omega along this line? Now, I claim, in fact, let's only query it along a line at some discrete set of points. So along this line, I'm going to query it at the point A, and then I'm going to query f of omega at the point a plus b, and then I'll query it at a plus 2b, and then a plus 3b, and so on. So what I claim is that this actually, the measurements that we observe from measuring f of omega at these points, it looks like a matrix vector product, where your matrix is a Vandermonde matrix, and your vector, has to do with the mixing weights in your mixture model. So to be precise, when I think about this exponential sum, remember that this f omega function, well, what it did was it put, it had e to the minus 2 pi I, and then it took the inner product of mu j and omega. And when I plug in for omega something like a, or a plus b, or a plus 2b, or a plus 3b, then there's some part that as I vary the constant in front of the b, I'm raising to a higher and higher power. That's where I'm pulling out this alpha sub j term, is it's the inner product between b and mu j. And I'm raising that to a higher and higher power as I look at successive measurements along the points along this line. And then I pull out the mixing weights, the lambda sub j's, along with the actual constant, the a that I started with. And that's exactly what I get, is that this is now, when I multiply this Vandermonde matrix times this vector of coefficients, I'm evaluating an exponential sum at these locations of omega. So that's mathematically what is going on in this problem, is that we're observing this Vandermonde matrix times this vector, And now we want to solve the inverse problem of figuring out what these mu sub j's are and what these lambda sub j's are. Okay, so this is really the last talk in the tutorial, so I don't want to get too technical. So I'm just going to assert that there is a beautiful algorithm out there called the matrix pencil method. In fact, just like Generick's algorithm, it's actually something that has been rediscovered tons and tons of times across different communities. It's kind of funny how often it's been rediscovered. And it's also like Generick's algorithms based on solving some generalized eigenvalue problems. Now, the catch is that it's something that's really designed to work without noise. So the basic theorem for the matrix pencil method is that when you have a sum of exponentials, and it's k exponentials, it turns out that you can evaluate that sum of k exponentials at any 2k plus 1 noise locations, provided you do it noiselessly. And there is an efficient algorithm to perfectly recover the parameters of the exponentials. You get the mixing weights and what actually shows up in the exponent. So that's really neat. But in our setup, noise is unavoidable because we only have access to a finite number of photons. We only get to record their location with some finite precision. And that's the main question, is really to understand how the sample complexity depends on k. So we don't want to work in this noiseless setup. We want to tackle head on what happens when we have noise. Now, you can ask the question, does the matrix pencil method work with noisy measurements? It turns out that the answer is, it works if and only if this generalized eigenvalue problem is itself somewhat stable. And a few years ago, I'd analyzed it for reasons that I won't get into this talk. But I showed that you can actually analyze the stability of the matrix pencil method. And it's stable if and only if the condition number of that van der Waals matrix is bounded. So that's the key point, is that when I described how the measurements we're observing look like a van der Waals matrix times a vector, then there is an algorithm to actually invert and solve what that mixture of exponentials looks like that works if and only if the van der Waals matrix isn't too close to being singular. So what we can show in our paper is that, let's say you started off with delta separated centers to begin with in 2 dimensions in this observation plane. And then you choose a random line and project onto that line. Well, then what's going to happen is that your minimum separation with high probability will only decrease in the sense that it'll go from delta to delta over k squared. And what you can do is you can show that the van der Waals matrix has a lower bound on its smaller singular value, that it's not worse than exponentially small in, let's say, k squared. There is, of course, some dependence on the minimum separation, because as you move some mu j very close to some mu I, then that means that 2 of the columns in the van der Waals matrix are getting closer and closer to each other, and you are getting closer to being singular. So the intuition for this is really just that the van der Waals matrix, it's oftentimes ill-conditioned. But when you only have k columns, it's not arbitrarily ill-conditioned. It's at worst exponential in k ill-conditioned. In fact, for those of you who don't think too much about these kinds of things, solving systems of linear equations in van der Waals matrices, that really has a lot to do with things like polynomial interpolation. So figuring out the coefficients of a polynomial, a degree k polynomial, only from being able to query it at some locations. These kinds of things you can do, and there's, you at worst exponentially blow up the noise. So what this lemma means for us is that all we have to do is we can try that strategy. We take our mixture of Airy disks, we try a line, and we project onto that line, and we get an exponential in k running time and sample complexity algorithm to learn the locations of the projections of the centers. And it turns out the way that you can piece together where the centers are in 2D is you can just try another line and stitch together which centers correspond to which projections. So now what I'm going to do is I'm going to take a step back and try and address really the most interesting question, which is, what happens in higher, what happens when you don't want exponential and k dependence. So the first thing that I want to mention is that actually it turns out that in 1D, the smallest singular value of a van der Waals matrix, it turns out that there are conditions under which the smallest singular value is not exponential in k small, it turns out that provided you have a separation condition, compared to some kind of cutoff frequency about how many rows you have in this van der Waals matrix, provided that the cutoff frequency is at least, let's say, 1 over the min separation, then you can prove a lower bound on the smallest singular value that's not exponentially small. So this is kind of neat. I'm not going to tell you how exactly this was proven, but it turns out that a key thing that's used in the proof of this is something called an extremal function. That if you take something called, if you take the sine function, SGN, so it's 0 when x is negative, and then it jumps up to +1, that's a very not smooth function. And what you can do is you can ask, well, is there a good smooth approximation? In fact, what you can do is you can ask, well, I want a function which majorizes it. So it's everywhere at least as large as the sine function. That function, this red function, should have the property that its Fourier transform is supported in the range -1 to 1. And among all such functions, I want to minimize the L1 distance between the red function to the black function. Now, it turns out that the exact optimal answer is known. It's called the Berling-Selberg majorant. And correspondingly, there's a minorant. And you can use these extremal functions as a way to precondition the van der Waals matrix to show that it's not exponentially ill-conditioned, provided that the separation is large compared to the cutoff frequency. So, we could hope for the same type of phase transition in 2 dimensions. Maybe if the centers are separated from each other in 2 dimensions, even though we only have band-limited access to the function, maybe it's possible that we can get a Paulian K running time and sample complexity algorithm. But there's going to be a big problem with this strategy is that I claim there are situations where you have point sources in 2D, but no 1D projection is going to work because it's going to destroy the separation too much. So let's think about this 2-dimensional problem. I claim that there are 2D configurations where there is no 1D projection that even approximately preserves the minimum separation without it reducing by something like a Paulian K factor. In fact, there's a really simple construction for that. I'm going to create pairs of point sources. They're going to be delta separated from each other. And then I'm going to create another pair that's far away, but I'm going to rotate it slightly. And then I take another pair and I rotate it slightly and so on until I cover all of the different angles. And now what happens is any 1D projection you choose, well, there will be a pair that almost collides on top of each other when you project onto that line. And in fact, this isn't just a failure of this technique of trying to reduce from the 2D problem to 1D. It's actually because the true threshold for the 1D problem is actually bounded above 1. So we actually proved that 1.15 threshold, that the true diffraction limit is actually strictly larger than it is for the 1D problem. So instead, we use a miracle, which is that it turns out through just sheer black magic to me, that there's been some very recent progress on understanding 2 dimensions and higher dimensional extremal functions. They nailed exactly what are the optimal higher dimensional extremal functions in the analogous way to the Berling-Selberg majorant in 1D. So there's a beautiful result of Goncalves, actually very recent from 2018, which shows that for some target radius r that again has to do with something to do with Bessel functions, well, there is a function m that satisfies the following 3 amazing conditions. So first of all, it's going to minorize the indicator function of the unit ball. That's similar to how we looked at majorants and minorants for the Berling-Selberg majorant. Now, we also want m to be a smooth approximation. So we want that when we take the Fourier transform of m, that it has bounded support. In fact, we want that its support is contained within a ball of radius r. So you get to choose an r between these 2 constants, which characterizes the smoothness of your function, at least in terms of its Fourier transform. And you want it to minorize the ball, but now you want it to, in some sense, be a non-trivial approximation. So you want m hat of 0 to be strictly positive. So this is kind of a mouthful, but let's just try and digest this by saying some trivial things. What if I ignored the third condition? So I want a function m of x that minorizes the indicator of the ball, it should have bounded Fourier transform. Well, if I ignore the third condition, then there's kind of an easy way to do that. M of x is equal to 0. That works, right? So the third condition says that I want to do strictly better than the all zero function. And what they know is they know the tight bounds on the radius where that is and is not possible. These are the optimal answers in 2D. And in fact, there's an expression in higher D for the optimal answer in higher D, where there is a non-trivial smooth minorizer for the indicator of the unit ball. In fact, these things really are black magic to me. So these bounds arise through the study of de Brange spaces of entire functions. If you understand that sentence, congratulations, you're probably a PhD in harmonic analysis. To me, these are just words. It's still a kind of mysterious thing what exactly this notion of de Brange spaces is and how exactly it leads itself to being able to analytically compute these optimal extremal functions. It really does look like a miracle to me. But it turns out that there's another strategy for learning exponential sums that doesn't require reducing to 1D. So there's an approach of Huang and Kakaday, whose approach is actually literally based on Jenrick's algorithm. And instead, what they need in order to apply Jenrick's algorithm and analyze its noise stability is instead they create a matrix that looks, it's not the Vandermonde matrix we saw before. It still has these exponential terms in here, but now instead of plugging in, omega and 2 omega and 3 omega, you're plugging in arbitrary values, omega sub 1, omega sub 2, all the way up to omega sub m. And what you care about is the condition number of this matrix. And it turns out that you can use these 2D extremal functions to give a tight bound on when random omega j's actually have bounded condition number, which is really neat. And what this tells us is that all of these things together, coupled with our lower bound of this 1.15, that's an explicit construction of things you can't resolve, is it shows us that a bunch of the purported diffraction limits, which were asserted as being the right constants, well, we can't pin it down exactly because it's still a rather challenging problem in harmonic analysis, but we can pin it down to a range that, the only things which survive this kind of scrutiny are Raleigh's condition and something called the Buxton condition, which is actually a fairly obscure one. And, let me just poke fun at Carol Sparrow. So this is with all due apologies to Carol Sparrow's friends and colleagues who clearly saw that the undulation criteria was the right one. It turns out to fall outside of the interval to which we can pin down the diffraction limit. So finding the sharp diffraction limit, I think, is a super interesting, very challenging question because I think it literally is equivalent to some type of problem in harmonic analysis about, optimal bounds for solving these inverse problems of exponential sums under, querying it only in bounded frequency locations. So let me just in the last 2 minutes, take a step back because this was something that I alluded to, but, in theoretical machine learning, we have lots of provable algorithms for some types of parameter learning problems. One that I've certainly spent a lot of my time thinking about are things like learning mixtures of Gaussians. And there's a nice story about how these arose way back in the 1890s in Carl Pearson's work, where he was studying some sort of biological statistics of Naples crabs. And he believed that it was explained as a mixture of two Gaussians. Now, in a lot of those settings in biology or when we apply it in machine learning, we don't literally believe that the problem is actually a mixture of two Gaussians because, a mixture of two Gaussians has infinite support. And I don't think that they're crabs whose forehead size is negative. So these are at best approximations to the data that you're observing. They might be pretty good fits in some contexts. And we have provable algorithms for learning these kinds of parametric models. But, I do spend my time sitting in a math department. And when I talk to applied mathematicians, they solve a lot of inverse problems with differential equations. And if you think about learning a mixture of Gaussians, it's like solving an inverse problem with the heat equation. Because you start off with some sort of nicer distribution, maybe if the two Gaussians are the same variance, you start off with two delta functions, and you convolve by a Gaussian, and that corresponds to taking that heat profile and running it forwards. And then you're really asking the question, if I observe this heat profile, what did it look like at some earlier time? So a bunch of our learning algorithms really are provable algorithms for some types of inverse problems on differential equations. And the same thing is happening here in optics. But what's kind of exciting is that, for an Airy disk, it's not really an approximation of the problem. When you have a star and you're observing it through a lens, it is actually an Airy disk that you observe. And in fact, your lens is basically spherical because they use all kinds of techniques to make the lens very, very spherical. The amount of deviation in its boundary between being a perfect sphere is just absolutely infinitesimal compared to the radius of the thing. So in optics, resolution is an inverse problem for a different kind of differential equation where the Airy disk is the thing that's the corresponding Green's function. And yet many of these ideas about how to provably deconvolve using the Fourier transform actually can be adapted. So let me end on this hopeful note, which is that, maybe there's more to do with these kinds of things, that maybe we're selling ourselves short. So when we have provable algorithms in theoretical machine learning, maybe there are ways to actually solve inverse problems in the sciences, particularly ones that come through differential equations. And maybe these kinds of insights about what we can provably do, what heuristics we can rigorously analyze, and what we can prove is just fundamentally off limits in terms of sample complexity are things that can really say something meaningful to these other communities that seem to me to be trying to solve related things. So let me stop there and let me summarize what I hope you got out of it. So the diffraction limit, even though you may not have thought about inverse problems in optics before, I certainly hadn't until I read this Nobel Prize citation for these super resolution cameras. Well, these are literally mixture model problems, and they're learning problems. That's what those inverse problems mean. And even though there were so many heuristic arguments for the existence of a diffraction limit, I think there's a huge value trying to put these on some rigorous foundations to try and understand fundamental limits in optics, particularly as a statistical phase transition, because I think statistical considerations aren't always things that arise in these debates. And, I'd love to see other people try and solve inverse problems in the sciences, which maybe might be amenable to other tools from theoretical machine learning, some of the types of things that I've discussed in this tutorial. So thanks very much, and happy to take any questions you guys might have.
Thanks, Ankur. So at this point, if you have a question that you'd like to ask out loud, please raise your hand and Nike will unmute you. But let's first try to handle questions from the Q&A.
Do you think the gap in the phase transition constants you derive is a statistical and computational gap? Or do you believe one of the sides isn't tight? So I don't believe that there's a computational versus statistical gap for this problem. That's a great question. But maybe your question gives me an opportunity to say something that I was supposed to say, but I forgot. So you see, when you have two Airy disks, there were tons of heuristics in astronomy for trying to deconvolve binary disk. And those heuristics were brute force search. You brute force search for the two centers and you check how well your fit is. And if it's a sufficiently good fit, you say, aha, that must have been the answer. If it's not, you say, maybe it's just one disk after all. But it turns out that, when you want to try and solve the problem for a larger number of centers K, that then, it's not just the sample complexity, but your algorithm would also be running in exponential and K time. So even if you were above the diffraction limit and you had some kind of separation among the centers, enough so that you in principle could get by with poly and K sample complexity, their heuristics still ran in exponential and K time. So when you talk about K being large, there is still the possibility, as you're pointing out, that there could be, it might be possible that you can do something in poly and K sample complexity, but maybe not algorithmically. I guess I'm just an optimist that, I think many of the tools for reasoning about why the problem is statistically well posed, they really have to do with creating test functions that precondition certain types of, matrices that have exponentials in them. And I think a lot of those preconditioners lend themselves to more clever types of greedy search. So this is really just a belief on my part that so far I haven't seen any techniques for reasoning about the statistical well-posedness that don't seem like they wouldn't also inform natural search heuristics within algorithms that avoid the exponential in K. Thanks. And Anna asks, is there a connection to the Heisenberg uncertainty principle? Absolutely, absolutely, absolutely. So let me actually just make sure that I've framed what the the Berling-Selberg majorant is properly. But see, the thing is that there are many different formulations of what the Heisenberg uncertainty principle means. And there are much simpler things that phrase the Heisenberg uncertainty principle in different ways that look more familiar for a physicist. So but let me maybe not get into those. But one way to phrase the the Berling-Selberg majorant is just that if you have bounded Fourier transform, you're bounded within your support is from -1 to 1, then your L1 distance to the sine function has to be at least 1, and it's achievable by the Berling-Selberg majorant. So you can think about this as some kind of if you're a good approximation to the sine function, then you must be spread out kind of thing. But it's a little bit more subtle to connect it really to the physics versions that you see in the Heisenberg uncertainty principle. We can talk more about that offline because I think maybe that wasn't the best answer, but.
So I had a question as well. So I guess that these problems are two-dimensional problems because your observation plane is two-dimensional. But I guess maybe there's a way to push the diffraction limit down if you have a third dimension as well.
So my sense is that the diffraction limit in 3D, depending on how you phrase it, would be larger. So I know that for these extremal functions that you get from these de Brange spaces, if you compute what's this critical radius where you have a non-trivial approximation, that threshold actually does get worse. And it kind of comes from the fact that you could embed this 2D thing into 3D arbitrarily. It's the same way that the way that we had this tight visualization of what these total variation curves looked like came from assuming that all the point sources were on 1D, which is a setting where we can actually perfectly resolve what the threshold is. This is 1. But the other thing that I should mention is that, what's kind of funny is, so this Goncalves paper, it's in the proceedings of the AMS, I think from 2018, and it has one citation, which is our paper. So, they studied this for very, very different reasons. And one of the funny things is that, you can study all different versions of these extremal problems in harmonic analysis. And instead of asking for majorizing or minorizing the L2 ball, you can ask it for the L infinity ball or things like this. And here there are super wide gaps between what is and isn't possible that have dimension dependence factors. So what's kind of interesting is that they study it for kind of different reasons within harmonic analysis. Actually, the original reason for the Berling-Selberg majorant was to use it in analytic number theory, because what you do is you don't create a smooth approximation of the SGN, the sine function. You create a smooth approximation to an indicator function of an interval, and you use that through an exponential sum to count how often primes modulo some constant land in the interval. And because it's a smooth test function, that becomes easier to use analytic tools. And the fact that it's sandwiching gives you a bound on the error guarantees. So what's really funny, and this is more maybe a wild pontification, but see, when I think about, all right, the matrix pencil method works when you have no noise. That's great, but it doesn't really tell you what are the real limits, because you only see the emergence of the diffraction limit when you add noise. And actually, you can see the same parallel in the way that number theory developed. A lot of the first tools were purely asymptotic, for how often, if you take an irrational number and you look at integer multiples of it, whether that modulo 1 becomes uniform along the interval from 0 to 1. And then people started asking questions like quantitatively, how close is it, and how fast does it converge to the to the standard density? And those types of tools end up being very useful, like quantitative bounds, to actually get stability bounds for us for how many samples do we need if we don't have an infinite number of samples. So I think a lot of these things are interesting, but it's kind of amazing to me that we need some versions of these extremal function problems. And they're studied in different communities, not because what we care, but because what's interesting to them for other reasons. So I find myself not knowing, in the extremal questions that I want to solve for learning problems, even having an idea of what it is that's in their wheelhouse that they might or might not be able to solve. And I don't understand de Brange's spaces, but if someone would like to explain it to me, I would love for that to happen. Is there a computer science equivalent to the second law of thermodynamics where effectively you just can't know the past from the knowledge of the present and you can't solve the inverse problem? Okay, so there's a lot going on in that question. So I'll say the following. So when people study it in applied math, like inverse problems with differential equations, they study it in a very different way, actually in step one, than the way that we do it in theoretical computer science. When we learn mixtures of Gaussians, we're solving an inverse problem with the heat equation. That's what it is. They solve inverse problems with the heat equation too, and they use Fourier transforms and they divide by the kernel. But the difference is the assumptions that you start off with. So for the most part, what they assume about the initial data is the exact opposite. So they assume that the initial data is smooth, maybe the right Sobolev space, that kind of thing. And we assume that it's not smooth at all. It's some sort of set of delta functions, but the key is that it's a parametric assumption because there are few centers. And really the theoretical computer science version of like which heat equations you cannot invert are the things which have too many parameters. It's a mixture of too many Gaussians, you cannot learn it. It's a mixture of too many Airy disks, you cannot learn it. And that's different than the versions in applied math that I see for the most part, which are this function is not smooth enough, so I cannot reliably invert the heat equation. So to me, that's one of the interesting things about how we pose inverse problems, is that they're set up in different ways. We start off with different kinds of assumptions. And I'm not sure there's a one-to-one marriage between the techniques, but I'd love to understand a dictionary of what things work and which things don't. There are also some really neat connections between things that go way back when to like Samuel Carlin called like total positivity that have a lot to do with what we do with like, those are other systems of functions that have the same types of unique interpolation properties as do, bounded degree polynomials. And that's something that I see much more in applied math happening, but I haven't seen this thought about within theoretical computer science.
So I have a minor technical question, if it's okay, which is that when you did before taking the Fourier transform, you did a kernel density estimate for your received points. But why do you need it? Because the Fourier transform of a sample.
That's a great question. So I didn't quite go into that because it would have been too many norms. But so if you have a smooth function rho of x, right, and it doesn't even matter what rho of x is, and you're in finite dimensions, because these things go out the window when you look at high dimensions. So now you take a bunch of samples from it that depends on your smoothness parameter, and then you convolve by a kernel density, by a Gaussian whose variance depends on the number of samples and your smoothness. And what you'll get is you'll get a good L infinity approximation.
Okay.
And that, when you take the Fourier transform, will transform into an L1. Exactly. So really, you just have to keep track of what's the right norm for your approximation. It's not actually important other than just working out all of the details, how they should work to be precise, because all of these things converge to zero and it doesn't really matter. It's good to do it with the right rates, but none of these things, because it's finite dimensions, actually matter very much.
I actually had a few questions, but it's kind of late, so maybe let me just ask one.
Yeah.
Do you have a good example of a deconvolution problem actually in high dimensions, like in practice, that people need to solve?
In practice. Practice is tough.
or maybe not high dimensions, but not too, more like
so I'm not sure all of them really. So I mean, I'll say that this optics problem, I think, is one of the simplest problems to try and make the connections between an inverse problem to the things that are studied within theoretical computer science, because it is a mixture model and it's the same type of thing we study. My sense is that a lot of the other inverse problems that we study and that people study in the sciences, they don't look like convolution or mixture models types of problems. A lot of them are, come from optics or like sort of having noisy 2D projections of 3D things, like that happens a lot in cryo-EM. So it just kind of looks a little bit different to me. But let me still try and give one interesting technical question. Now, I'm not sure it's going to fit the bill of being a practical thing per se. But one of the things that people do care about is, back in my first lecture, I talked about, algorithms for learning mixtures of Gaussians. Now, one of the things that people study is, can you learn mixtures of Gaussians just on a separation condition on the centers? And there's been a lot of progress that, for the longest time, the best known bounds were actually k to the 1/4. If you have k different, Gaussians and they're spherical in n dimensions. And that threshold came from just some concentration of measure types of things. Because when you have, 2 Gaussians in like n dimensions, when they're like n to the 1/4 separated, that's when a sample from one will be closer to its center than it will be to the other center. And it just has to do with the overlap. So the k to the 1/4 came from the fact that you find the space where all the centers live in, the k-dimensional space, and you use that same separation condition. Now, through sum of squares, people have gotten the separation condition down to k to the epsilon. But in principle, you could actually get it down to root log k. And that's the optimal bound information theoretically. And one of the things that I wonder is, when they're all actual spherical Gaussians, it is a deconvolution problem. And this is usually used as a proxy for like how well can you solve a clustering problem from some generative model. And for that type of thing, what you really need is you need some types of functions that you can divide by that sort of have some very steep decay, but have bounded Fourier transform. And what's kind of amazing is that there's an entire theory for studying if I have bounded Fourier transform, what decay rate can I get in the limit? Because that's Berling-Malieven theory. But what's not known are effective bounds on how quickly they decay for finite bounds instead of in the limit. So I don't actually know the answers to that, but specifically for these extremal function problems that come through de Brange spaces, these things are known really through a miracle. Like I don't understand it and I haven't yet figured it out. So I would say that there are learning problems from simple generative models where, creating good test functions might actually have something to say about, can you cluster under much weaker separation conditions, potentially.
Cool, thanks.
But unfortunately, I've never taken an analysis course in my life, so I don't know any analysis.
I think there are some related questions in convex geometry that, okay, I mean, some of the same spirit, kind of, you have a convex body that you have some distribution that's supported inside it, and you want to prove bounds on, the Fourier transform can't be supported in the dual of the convex body, stuff like that.
And are some of the tools
really
from
related, but just of the same spirit?
So the Berling-Malieven theory, as far as I can tell, it's through these multipliers, like Fourier multipliers techniques, and it seems very ineffective sort of fundamentally for the tools, but it's kind of tricky because there's so many proofs of these facts. But maybe for some of the like high dimensional convex geometry, some of those things I imagine might be more effective or quantitative than the things that are known. Or neat. I'll have to ping you for some references. Would this be an approach to get sub-quasi polynomial time algorithms for spherical mixtures at separation square root log d? Yes, that's why I asked it. Thanks.
Any more questions? Okay, so if not, thanks again, Ankur, for this excellent lecture series. Thank you to all of the speakers in the boot camp. It's been a really exciting 8 days. And with this, we conclude the boot camp series for the high dimensional program. So thank you very much. We'll have one last coffee break in the Gather Town.